Algebra. We're up to lecture 17 out of 28 classes. And we've been talking about group theory. So let me review a little bit what we did on Monday, and we will then move forward from there. So we have a group G, a subgroup H, and we defined a relation on G as follows. X is related to Y. So this is for all elements X and Y in the group. You say X is related to Y if X inverse Y is in the subgroup H. And the equivalence classes of this relation are the left cosets. So the left coset XH, so H is the subgroup, X is an element in the group. This is the set of elements of the form X times H, where H is in the subgroup capital H. That's a left coset. And we have another relation where we say, in this case, X is related to Y if Y X inverse is in H. And again, it looks like I'm just multiplying the same things, but here I'm multiplying X inverse times Y. Here I'm multiplying Y times X inverse. And in general, in a group that is non-abelian, these are different elements. So this is an equivalence relation. And the equivalence class are the right cosets. H times little x. So this is everything. This is the set of elements of the form H times X for all H and H. X is fixed. And by G mod H, this is the set of left cosets of H in G. And H slash G written like this is the set of right cosets of H and G. Right? So this is, in a sense, an abstract definition, but it is one of the fundamental definitions in group theory. And in the exercises, there'll be various examples where you have to actually calculate what these right and left cosets spaces look like. The fundamental theorem that we proved already twice, so I'm not going to prove it again, is Lagrange's theorem. So the theorem of the French mathematician Lagrange from the 19th century says the following. If G is a finite group and H is a subgroup of G, then the number of left cosets is the same as the number of right cosets. It's the order of the group G divided by the order of the subgroup H, where when I put absolute value signs around a set, it means the number of elements in the set. So that's a really major theorem. And we call this integer, which is the number of left cosets, the index of the subgroup H and G. And it's denoted G colon H square brackets around it. Okay. So for example, if G is S3, the permutation group, and H is the subgroup consisting of the identity, and let's say just the transposition 1, 2, then the index of H in S3 is the order of S3 over the order of H. The permutation group S3 has 6 elements, H has 2 elements. 6 over 2 is 3. So the index of this subgroup is 3. If we take G to be the integers and H to be the set of all multiples of M, then, well, I'm sorry, this is a nice example, but it's doesn't, I don't want to use that because this is an infinite group. If we take, let's say, Z mod 8Z. So what is this? This is the congruence classes mod 8. It's all congruence classes A plus 8Z, where A is an integer from 0 to 7. These are the congruence classes mod 8. So that's my group G. This group has 8 elements. If I take H to be the set of 2 cosets, 0 plus 8Z and 4 plus 8Z, this is a subgroup of order 2, because this is a subset of this group, that is, it consists of congruence classes mod 8. It's closed under addition because 4 plus 4 is 0 mod 8. And so the order of this group is 2. And so the index G mod H is 8 over 2. That's equal to 4. And what are the cosets? G mod H. So I have H, two plus 8Z plus H. Sorry, not 2. One plus HZ plus H, 2 plus 8Z plus H, 3 plus 8Z plus H. And let me spend a little bit of time just explaining this example. So Z mod 8Z, this is the congruence classes modulo 8. So we have the congruence classes A plus 8Z, and a complete set of representatives of these is A is 0, 1, 2, 3, 4, 5, 6, or 7. These are the 8 congruence classes mod 8. And addition, the sum of 2 congruence classes is the congruence class A plus B plus 8Z. And this is the example we've looked at many, many times. Now, suppose I take H to consist of 2 congruence classes, 8Z, which is 0 plus 8Z, and 4 plus 8Z. This is a subgroup of G. And in fact, what is the addition table for this subgroup? I have 8Z, 4 plus 8Z, 8Z, 4 plus 8Z. This is like 0 plus 0. If I add this, I get 8Z. 0 plus 4 is 4. 4 plus 0 is 4. 4 plus 4 is 8, and 8 is the same as 0 mod Z. So this is the addition table. If I wanted to simplify my notation and let A bar be A plus 8Z, then in the subgroup H, the two elements are 0 bar and 4 bar. And 0 plus 0 is 0. 0 plus 4 is 4. 4 plus 0 is 4. 4 plus 4 is 8, which is the same as 0. So in slightly different notation, this is two ways to write the addition table. And what is a left coset of H? So suppose I take the coset x plus 8z plus h. What is that? So this is x plus 8z plus every element in H. What are the elements in H? H has two elements. In fact, maybe just to make it so there's less writing and maybe it's clearer. So x plus hz, x plus 8z, again, this is x bar. So H consists of two cosets, 0 and 4. And x bar plus h, this is x bar plus 0 bar, x bar plus 4 bar. That's equal to coset of x and the coset of x plus 4. That's what's in this left coset. So for example, 1 plus h is 1 and 5. 2 bar plus h is 2 and 6. 3 bar plus h consists of the two cosets, 3 and 7. And of course, this is h, 0 and 4. So you see, if this is the group Z mod 8Z, there are 4 cosets. I have H, 1 plus H, 2 plus H, and 3 plus H. This is 0 and 4, 1 and 5, 2 and 6, 3 and 7. You see all 8 congruence classes are listed here, but they're in pairs or by cosets. 1 coset, 2 coset, 3 cosets, 4 cosets. And again, the index of H in Z mod 8Z, this group has 8 elements, this group has 2 elements, 8 over 2 is 4, and we have 4 cosets. Okay. Any questions about this? Now, when we were looking at congruence classes, we saw that the set of congruence classes itself forms a group. The additive group of congruence classes modulo H. And I want to show that there's a similar kind of construction when you have a group and a subgroup, so long as the subgroup satisfies a certain very nice property. So we say that, so if you're looking at the notes, or if you look at the notes, this is on page 15 of the lecture notes on group theory. So a subgroup H of G is called normal if the left coset XH and the right coset XH are equal. This set is the same as this set for all elements X in the group. And there is a very, very useful lemma in the notes. This is called a theorem. So this is Theorem 5 in the notes. We have H, a subgroup of the group G, and then the following statements are equivalent. So the first says that the left coset XH is contained in the right coset XH for all X in the group. Second is stronger. It says the left coset XH equals the right coset XH for all X in G. And remember, this is the definition of a normal subgroup. The third set says if you take XH, that set, and you look at all products with the left coset YH, you get another coset, namely the coset XYH for all X and Y in G. The fourth says if I take the set XH X inverse, this is contained in H for all X in G. And the fifth says that XH X inverse equals H for all X in G. And just as a definition, XH X inverse is called conjugation of the set H by X. So if you conjugate by X, if you conjugate a set H by X, you form the new set whose elements are everything of the form X times an element of H times X inverse. That's conjugation. So how do we prove these statements? We actually have to prove 5 things. We have to show 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 goes back and implies 1, or some variation of those things. So proof. Suppose XH is contained in HX for all X. Then we also have choosing X inverse for X, X inverse H is contained in H X inverse for all X. So I can put this together and we can say the following. So I want to show that if the left coset is contained in the right coset, in fact, the left coset equals the right coset. So suppose I take the right coset HX. So this is the same as the identity times HX. Again, this is a set. This means multiply everything in H by X. This means multiply everything in HX by E, but multiplying by the identity just brings you back, gives you the same set. But of course, E, I can write as X times X inverse times HX. And by associativity, this is the same as x inverse h times x. And x inverse h is contained in hx inverse. So this is contained in x, hx inverse times x, which is xh, x inverse x, which is xh times the identity, because x inverse x is the identity. So this is xh. So therefore, I prove that x, the right coset, is contained in the left coset. So what I've just shown is that if the left coset is contained in the right coset, then the right coset is contained in the left coset. And you put these together, if you have two sets and each is contained in the other, then the sets are equal. So that's a proof that 1 implies 2. Right. Any questions about this? This is the kind of reasoning that you have to master in algebra. Okay. So let's prove that 2, which is the statement xh equals hx for all x, implies what I wrote down as 3, which is that if I take the left coset xh and I take the left coset yh and I take the product of these two sets, I get the left coset xy times h. So it's a simple fact that if you look at the set h times itself, this is h if h is a subgroup. So suppose I take xh times yh. Again, let me just write down explicitly what this means. Xh is the set of all x times h for h in h. And I'm multiplying that by the left coset yh. Maybe I'll call this h1. The set of all things of the form yh2 for all h2 in h. When I multiply these sets, it's all products of something here times something here. So it's all elements of the form xh1 times yh2 as h1 and h2 independently run through all elements of h. I can think of this as everything of the form x times h1y times h2, where h1 and h2 run through h. So this is like h1y, as you run through all elements of h, that's just the coset hy. And I'm multiplying that on the left by x, and I'm taking all products of that with, again, with the elements of h, that's equal to this. This is really just the kind of associativity. xy times yh is x hy times h. But we have xh equals hx for all x. So in particular, hy equals yh. So I plug that in here. This is x. Hy is the same as yh times h. That's xy times h. But h times h is h. So this is xy times h. And that's the end of the proof. Of that part. So that says 2 implies 3. So again, what this shows is, so I want to show 3 implies 4. I just showed that xh times yh is xy times h for all x and y. So suppose I let y equal x inverse. Then I get xh times x inverse h is x inverse h, which is h, because x inverse is the identity. So another way of saying this is that xh x inverse times h is contained in h, and one element in h is the identity. So xh x inverse is contained in h. So that's what I wanted to prove. That's statement 4. That if I take any subgroup H and I conjugate it by any element of X, that's contained in H. So 3 implies 4. And there are 2 more things. Let me see if I can squeeze them in on the same piece of paper. 4 implies 5. So I know xh x inverse is contained in H. So if I replace x by x inverse, I get x inverse h, x inverse inverse, which is h, x inverse inverses, the inverse of x inverse is x, is contained in h. If I multiply on the left by x and on the right by x inverse, I get h is contained in xh, x inverse. So if xh, x inverse is contained in h, then h is contained in xh, x inverse, and these 2 have to be equal. And that's part 5. And finally, to show that statement 5 implies the first statement, if xh, x inverse is contained in h, then if I multiply everything in this set on the right by x, it's contained in what I get by multiplying everything in this set on the right by x. But x inverse x is the identity, so this is xh. So the left coset's contained in the right coset. So this is theorem 5 on page 14, and it's extremely difficult when you're seeing this for the first time to follow what's going on in sort of the lecture in front of you, which is why you need to spend a lot of time at home studying the notes, I guess. Yeah. So now we're ready to construct the quotient group. So let me just go through this in the order in which I wrote it down. So theorem 6 says H is a subgroup of the group G. So coset multiplication, that is, if we want to define the product of xh and yh as xy times h, this is well defined if and only if h is a normal subgroup. So the proof in one direction I just did. So H normal implies coset multiplication is okay, well defined. But conversely, if XH times YH equals XYH for all X and Y, then XH equals HX for all X, and H is normal. So this is all built into the lemma I just proved. So this notion of coset multiplication works if and only if H is a normal subgroup of the group G. So the big theorem I will give it a star. Theorem 7. So it says the following. If H is a normal subgroup of the group G, then the set of cosets G mod H, and if H is normal, the left cosets are equal to the right cosets, is a group with the binary operation XH times YH defined to be XYH. And the identity element in this group is EH, the left coset of the identity, which is just the set H. So the proof now is very straightforward, at least once you're familiar with algebraic reasoning. Suppose I want to prove associativity. So if I take XH times YH and I multiply by ZH, what do I get? XH times YH is the coset XYH times ZH. So that's the coset XY times ZH. But this element is the same as X times YZH, which is the same as XH times YZH, which is the same as XH times YH times ZH. So that's the proof of associativity. And in terms of the identity, XH times H is XH times EH, which is XE times H, which is XH. And EH times XH is EX times H, which is X times H. Right. So this EH or H is the identity on the left and the right. And if I take the coset XH and multiply it by the coset X inverse H, I get X times X inverse H, which is E times H, which is H. And similarly, if I multiply in the opposite order, X inverse H times XH is X inverse XH is EH equals H. So I've just proved that the three axioms, the three parts of the definition of a group are satisfied for this group of cosets. And this group is called the quotient group.
Professor, do you mind just keeping it there for half a second? Sorry, thank you.
Okay. But again, everything is written out legibly in the notes. This is on page 15 in the notes on group theory that I posted on Blackboard a few weeks ago.
All right, all set. Thank you.
So this group G mod H, when H is a normal subgroup, has a name, and it is called the quotient group of G by the subgroup H, because you're sort of dividing G up into pieces, which are the cosets of H. So let's look at an example or several examples. So a few minutes ago, I looked at the congruence classes mod 8, and then our H be the subgroup consisting of the congruence classes of 0 and 4, where X bar means the congruence class X plus 8Z. And what are the cosets G mod H? They consist of H, 1 plus H, 2 plus H, and 3 plus H. Okay. The order of G mod H is the order of G over the order of H, which is 8 over 2, which is 4. And in an abelian group, X plus Y equals Y plus X implies every subgroup is normal. This is a normal subgroup. So here I have this is a new group. This is the quotient group. And what is the addition table? So I have 4 elements in this quotient, 0, 1, 2, and 3. And how do I add? So this is in G mod H. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. But the congruence class of 4 equals the congruence class of 0. Right? Or the coset 4 plus H is 4 plus 0 and 4 plus 4, which is 4 and 8. But 8 is the same as 0 mod 8. So this is H. 0. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 4 plus H is H. That's giving back 0. 2 plus 3 is 5, which is the same as the congruence class of 1. 5 plus 0 is 5. 5 plus 4 is 9 is 1. 3 plus 0 is 3. 3 plus 1 is 4 is 0 here. 3 plus 2 is 5, which is 1. And 3 plus 3 is 6, which is 2. I should actually be a little bit more careful here. So G mod H consists of these congruence classes. So this is really the coset 0 bar plus H, 1 plus H, 2 plus H, 3 plus H. So what I'm adding are cosets in the quotient G mod H. The cosets are, I have the subgroup H and I translate it by 0, 1, 2, or 3. And these are all plus H. Two plus 3 is 5 is 1. 3 plus 3 is 6, which is 2. So let me just emphasize this. What is 2 plus H? This means this is the congruence class of 2 plus, and what's in H? 0 and 4. So that's 2 plus 0 and 2 plus 4. That's 2 and 6. The congruence class of 2 and the congruence class of 6. What's 6 plus H? That's the congruence class of 6 plus 0 and 4. That's 6 plus 0 and 6 plus 4. These are congruence classes mod 8. This is the congruence class of 0. 6 plus 4 is 10. But 10 is congruent to 2 mod 8. So the congruence class of 10 is the congruence class of 2. And again, so the left coset 2 plus H is equal to the left coset 6 plus H. They both consist of these two congruence classes. Let's look at another example. So let me just make this following remark so it's explicit. In an abelian group G, every subgroup H is normal. Because if you take the left coset XH, this is the set of all elements of the form X times H, where H is in H. But XH equals HX for all H and H, because that's what abelian means. The order of multiplication doesn't matter. So XH is the same as HX. So this is the right coset, XH. So in an abelian group, every subgroup is normal. Suppose I let G be what I write as Q, which is the rational numbers. That just means fractions. So this is an additive abelian group. Suppose I take the subgroup of integers. I take H to be the subgroup of integers. Every integer is a fraction with denominator 1. Every integer is a rational number. So if I look at Q mod Z, this is the set of all cosets X plus Z, where X is a rational number. This is an infinite group. So Q is infinite, Z is infinite, and the quotient group is infinite. And we can say that the coset X plus Z equals the coset Y plus Z if and only if X minus, just subtract them, if and only if X minus Y plus Z equals Z, if and only if X minus Y is in Z. That means X minus Y is an integer. And there's a pretty picture of what this quotient group looks like. So 0, 1, 2, 3, 4, minus 1, minus 2. Let's say I take a number x between 0 and 1. If I look at the number x plus 1, the difference is 1. It's an integer. So x plus 1 is in coset of x. And similarly, x plus 2, x plus 3, x minus 1, x minus 2. If I just take this point and just look at all of its images periodically as I move to the left and the right, shifting by 1, this whole infinite set is the coset. That is, x plus z is equal to x plus n for all integers n. That means x, if I take n equals 0, x plus 1, x plus 2, x plus 3, and so forth, x minus 1, x minus 2, x minus 3, and so forth. So that is the coset. This coset is infinite. It's all translates of the rational number x by a whole number. Okay. Any questions about any of this? Let's go back and say a few simple things about groups. Suppose G is a group, and we have a family of subsets. H sub I, indexed by I, like H1, H2, H3, and so forth. Then, if I take the intersection of these subgroups, H sub I, and I, as I look at everything that belongs to all of these subgroups, this is a subgroup also of G. So the intersection of subgroups is a subgroup. And the proof goes as follows. Let me call this H, that X and Y be in H. So then X and Y are in HI for all I in this index set, capital I. And each of these is a subgroup. So X times Y is in HI for all I. So XY is in the intersection of H sub I. So H is closed under multiplication. We have the identity is in every group. So the identity is in HI for all I. So the identity is in the intersection of all the H sub I's. So H contains the identity. And if X is in H, which is the intersection of all these subgroups, then X is in H sub I for all I. And each of these is a subgroup. So X inverse is in HI for all I. So X inverse is in the intersection of the HIs, which is H. So that's the end of the proof, because if I take the intersection of subgroups, it's closed under multiplication, it contains the identity, and it contains the inverse of each of its elements. So let S be not a subgroup, but be a subset of G. And suppose I let I don't know what to call it. I'll call it. So consider the set of all subgroups H sub I in G that contain the set S. For example, G is a subgroup of itself. It contains S. So if I look at all subgroups of G that contain S, that includes G. And I'll write sort of like S with brackets around it here. That this be the intersection of all of these subgroups contained in G that contain S. So this is an intersection of subgroups that contains S, and this is called the subgroup of G generated by S. So, which is also, so this is in fact the smallest subgroup of G containing S. So for example, if I let G be the integers and S to be the set just consisting of the number 3, then the subgroup generated by 3 is just all multiples of 3. Because if a subgroup contains 3, it contains all multiples of 3, and that itself is a subgroup. If I take G equal to Z and S equal to, let's say, 5 and 7, then the subgroup generated by S, it has to contain all multiples of 5 and 7. One such multiple is 1. So this is the whole set of integers. So the subgroup of the integers generated by the set consisting of just the two numbers 5 and Z is Z, right? Because 5 times 3 plus 7 times minus 2 is 1. So 1 is in this set. So every integer is in the set. So I have already discussed the commutator of elements in a group. The commutator xy of elements x and y in a group is the element x comma y equal to x inverse y inverse xy. And I can look at all the commutators in my group and what we call the commutator subgroup of G is the subgroup of G generated by the set of all commutators. So it's the smallest subgroup of G that contains every commutator. And we saw that the commutator of x and y is the identity if and only if x and y commute. And that leads to the following theorem. I mean, groups are very complicated. Abelian groups are a little bit simpler than ordinary groups. And so suppose we have H, a normal subgroup of G. When is the quotient group abelian? It's abelian if and only if the subgroup H contains the commutator subgroup of G. So let's look at the proof. So G mod H is abelian means XH times YH equals YH times XH for all X and Y in the group. This is the same as saying XH times YH is XYH equals YH times XH is YX times H. Multiplied by Y inverse, multiplied by X inverse. So what I have over here is the commutator of X and Y times H, this left coset. The Y's and the X's cancel equals H. So the left coset of H equals H if and only if this element, XY, is in H. So this says that the quotient group is abelian if and only if H contains every commutator, which is the same as saying H contains the commutator subgroup of G. So that is a nice example. Of course. If G is abelian, that means every commutator equals the identity. Which this is the same as saying X and Y commute. So G mod H is abelian for all subgroups H, because again, this is the same as saying the commutator subgroup of G is just the trivial subgroup consisting of the identity element and nothing else. Because every commutator is the identity, so the set of commutators is just the identity, and that's a subgroup. And there's a very nice remark that I can put in here in the notes. This is Theorem 10. So I have G a group, H a subgroup. If the index of G and H is 2, then H is a normal subgroup. And what is the proof? So if the index of G and H, of H and G is 2, that means the number of left cosets and the number of right cosets is 2. So here I have my group G. I have H, and there's only one other left coset, say XH. So this is the left cosets, G mod H. But I also have the right cosets. One of them is H, and X is not in H, otherwise XH would be equal to H, so this has to be HX. So this left coset XH is everything in G that's not in H. The right coset HX is everything in G that's not in H. So the right coset equals the left coset for all X in the group. So if the index is 2, this means the subgroup is normal. And any group with 2 elements is abelian. If you have a group with 2 elements, E and A, E times E is E, E times A and A times A is A. A times A is not A, it can only be equal to E. That's an abelian. So every group with 2 elements is this very simple group. Okay, well, there's a little bit more theoretical material in this section in the notes, but let me look at some examples. So I have the group S3. So this is the symmetric group. It has the identity sigma sigma squared. Remember, sigma is the notation I've been using. The cycle 1, 2, 3, sigma squared, which is the cycle 1, 3, 2, which is also sigma inverse. And I have 3 transpositions, tau 1, tau 2, and tau 3. Tau 1 fixes 1 and switches 2 and 3. Tau 2 fixes 2 and interchanges 1 and 3. Tau 3 fixes 3 and interchanges 1 and 2. Now, if I let H be the subgroup generated by sigma, so if it contains sigma, it has to contain, if it's a subgroup, it contains the identity sigma and sigma squared. This is the subgroup generated by sigma. It's these 3 cycles. The identity, 1, 2, 3, and 1, 3, 2. So the group S3 has 6 elements. The group H has 3 elements. So the index of H in S3 by Lagrange's theorem is 6 over 3, which is 2. So H has index 2. If H has index 2, that means H is normal. So S3 mod H is a group with 2 elements. So what are the elements? First of all, I have H. Which is this subgroup. And if I take any thing not in H, like for example, I take tau 1 times H. What is tau 1 times H? What is that left coset? That means I take tau 1 times every element of H. Tau 1 times the identity, tau 1 times sigma, tau 1 times sigma squared. That's what's in tau 1H. let's do this calculation. I've already done it, but let's do it again. So tau 1 times the identity is just tau 1. That is the permutation 2, 3. What is tau 1 times sigma? That's the transposition 2, 3 times the transposition sigma is 1, 2, 3. What is this? 1 goes to 2, 2 goes to 3, so 1 goes to 3. 3 goes back to 1, 2 goes to 3 goes to 2. So tau 1 sigma is this transposition, which is tau 2. Tau 2 sigma, tau 1 sigma squared is 2, 3 times 1, 3, 2. So this sends 1 to 3 to 2. This sends 2 to 1. This sends 3 to 2 to 3. So this is the transposition 1, 2. This is tau 3. So tau 1h consists of tau 1 times the identity, that's tau 1. Tau 1 sigma is tau 2. Tau 1 sigma squared is tau 3. So this is the second element in S3 mod H. So S3 mod H consists of two elements, H and tau 1h. H is E sigma and sigma squared. Tau 1h is tau 1, tau 2, tau 3. So if we look at the group S3, I have E sigma and sigma squared. That's in one left coset, H, and tau 1, tau 2, tau 3. That's in the other left coset. So S3 mod H has two elements. This set is one element. This set is the other element. All right. Any questions about this? The problem, of course, is we don't have many groups at our disposal very easily. Let's see. What are some other group stuff we have? Suppose I take the cyclic group, gamma n. So by a cyclic group, this is a multiplicative group generated by some element I can call A. So gamma n consists of A, E, A squared, A cubed, up to A to the n minus 1, where A to the n is the identity. And in fact, if you multiply A to the k times A to the L, that's A to the k plus L, which is really A to the m, where k plus L is congruent to m mod n. Because A to the n is the identity. So suppose I take D, a divisor of n. The subgroup generated by A to the D consists of all powers of A to the D. E, A to the D, A to the 2D, A to the 3D. How far up do you go? If D is a divisor of n, then n is equal to D cubed for some integer q. So I can go up to A to the q minus 1 times D, but the next power of D is A to the QD, which is A to the n, which is the identity. So this is the cyclic subgroup generated by A to the D. And this cyclic subgroup, the order is Q, which is N over D. So let's call that H. So and this, everything is abelian, so this is a normal subgroup. So gamma N mod H, it's all the left cosets, A to the I times H. And how many of these cosets are different? A to the I H, this is A to the I times this set E, A to the D, A to the 2D, up to A to the Q minus 1 times D. So this is, if I multiply each element by I get A to the I, A to the D plus I, A to the 2D plus I, up to A to the Q minus 1D plus I. It's these Q elements. So for example, if I equals 1, AH is A to the D plus 1, A to the 2D plus 1, up to A to the Q minus 1D plus 1, and so forth. And the quotient group, gamma N modulo this H, consists of the left cosets, A to the I H, where I goes from 0 up to D minus 1. And if you examine this example and you compare this to gamma N is like the integers mod N, and H is like the subgroup generated by I plus NZ, you get a very close analogy or even isomorphism between subgroups of Z mod NZ, which is also a cyclic group written additively instead of multiplicatively, and the subgroup generated by the congruence class I plus NZ is completely analogous to the powers of A to the I. D plus NZ, the multiples of D. The multiples of D of congruence classes modulo N are analogous to the powers of A to the D in the cyclic group. Whew. Okay, well, that's a fair amount to think about. Yeah. So what I covered today is in the lecture notes that I posted. It's section 3 on normal subgroups and quotient groups. And it's about 4 pages, but there is a great deal of material there. This is dense, as they say. And so it's worth spending a fair amount of time working through this as carefully as you can and coming back with questions. And I will post some homework about normal subgroups and quotient groups tonight, and that'll be due next week. Any questions about what we've been doing? No. All right, so I don't want to press ahead too fast, and you really do need time to study the material, study the notes. It's also discussed in the textbook, the Dover paperback that we use, but it's much more concise. You might think this is concise, but it's much more concise in that book than it is in my notes. Any questions before we quit for the morning? I have an office hour this evening, and you are welcome to log on and ask questions or ask for more explanation of what we've been doing. Okay, if there's nothing else, then we are done for now. Take care all.